I've been told to introduce myself. So hi, my name is Sam Engblom. I am a recently minted PhD from the University of Illinois. I teach at the University of Illinois as a postdoctoral scholar in physics. And the things that I tend to study are how people teach and how people learn, specifically in the context of physics and mathematical reasoning and pedagogies and teaching approaches for those types of classes. So I'm here today to talk to you about something that I called units of thought, agents of mind, which is this idea of the resource model of human cognition. There's a lot of context that I'm going to set for you to get to talking about this, because these things are messy and empirical, and we have to think a lot about a bunch of different things. But I'm hoping that all of the things that I show you along the way are at least somewhat interesting. That being said, I have teaching instincts, which means that I have habits that I cannot get rid of. And one of those habits is that I have a question, and it's a physics question, and I want to ask everybody this. Someone has said before the presentation that they think they know the answer to this. If you know the answer and you are super confident in the answer, I need you to pretend like you don't know. So this is a thing that, this certainly occurred to me at one point, but this has been a question that people have asked at various points, which is that if you've ever ridden a bike, rode a bike, one of the things that you know to be true is that when you are moving forward, it is much easier to balance than if you are just sitting on the bike, not moving anywhere. And my question is, why is that? Why are bicycles so easy to balance when they're moving, but so hard to balance when they're standing still? I see a hand. Guess what? I'm gonna take it one step further, and I'm going to make everyone talk about it. So this is where my teaching instincts die hard. In groups of 2 to 3 with your neighbors or the nearest person to you, find people to talk to. You can go up to 4 if you need to. And I want you to discuss for like 5 or 6 minutes. Tell me, what's your best theory for why this is true? Ready? Go. You have to do it too. My first move is to get more coffee. What do you think? How are you doing today?
Okay.
I'm okay too.
I have not a clue as to why. Yeah, I know it's true.
From like personal experience. I haven't ridden a bike in a long time. I don't own one anymore.
There's one in my garage, but I don't ride it. I rode it out in traffic. On a road, it wasn't very heavy traffic. You don't belong out here.
Yeah.
I can ride one, but getting stopping and starting.
Yeah. Yeah. I told somebody, I was like, I have a PhD in physics, which makes me feel like I should know the answer to this question. And I thought I knew the answer to this question. And then I found out that I was wrong. It's actually it's not what you'd expect, but it's not that difficult. So the thing that I thought it was that in your physics class you learn that wheels that are spinning have something called angular momentum. And so a thing that's spinning kind of wants to keep spinning in the same kind of plane that it exists in. And if you start to tilt it, it wants to go back. So I thought that was what it was, and then it wasn't. All right, I'm gonna go see what people say though. Okay. Am I still able to be heard?
Yes.
Good. Okay. I sat on the box. Did you see this? I sat down on the mic. I was afraid that I broke it. All right. So that was about 5-ish minutes, maybe? Enough time for me to go get more coffee. I'm interested. Are there like 1 or 2 brave groups that are willing to share their ideas?
For a fee.
I don't make that much. All right. So will someone do it for free? For a cookie? That's acceptable. I'll go up here first, and then I'll go back there second, if you're willing. Go ahead. What?
We have a disagreement,
Okay.
and we've each read that the gyroscopic effect of the wheels helps keep the you going in a straight line and upright.
Hey.
And I have read that, and I like it, but I disagree because when you go really, really slow, you're still able to keep that bicycle aligned, and I can't believe there's enough gyroscopic effect there or other things to account for keeping it.
All right. Okay. I'm going to revoice what you said, and you're going to tell me if I get it right. So this group in the front has proposed that something called gyroscopic motion. Did I get that right? Yeah. Is responsible for keeping the bike upright. So that's this idea, like in physics, it's this idea that something that is rotating really wants to kind of keep existing in the same plane that it's rotating, and turning it off of that plane, like kind of falling over on the bike is harder because you have something that's spinning quite quickly. And this gentleman on the far, on my right, your left. What's your name?
John.
John? John has suggested that he doesn't quite agree, and there's been a disagreement in this front group. Drama. It's great.
We were going to fight.
You were ready to? Okay. Well, it's good that I stopped you when I did. So, John has noted that when you're not moving very fast on a bicycle, you still stay upright. Now, if you know anything about gyroscopic motion, it's a function of how fast things are spinning. So fast wheels should do more to keep you upright than slow wheels. But even if you're pedaling very slowly, it is still easier to balance than it is if you're sitting still. Any other thoughts? I'll go back. What do you think?
Well, I think he's right. It's the gyroscopic effect of the wheel. I don't know why that makes it easy, but it does.
Mm-hmm.
And I'm at inertia. If you're moving forward, there's the motion to stay in motion. So,
All right. That's a classic one. So we're now adding 2 things together. Gyroscopic motion seems like a compelling idea, but we're also adding in, well, if you're going forward, you should stay going forward. All right. Librarians in the back. The defenders of wisdom in our society.
Our first thought was just the word motion, was as far as we could get it first. But then I also wondered about weight and kind of where, like center of gravity.
I see. So, I suspect that where you're going with that in terms of motion and weight moving is an argument that's really similar to this gentleman in this group and kind of the front tables in the back here. That like really this is about like inertia. Getting something moving means that it's more likely to stay moving. Do I have to pay?
0.
Okay, well if I have to pay, I'm not taking the comment.
Well, you want my answer?
Yeah, let's hear it.
Well, if your bike is standing still, you have a high center of gravity.
Mm-hmm.
If you move forward, you lower your center of gravity, which makes it much easier to balance.
All right, so it has to do with the height of the center of gravity. The higher your center of gravity, the harder it is to balance. And if you're moving, it's lower.
Yes.
Yeah, that's another classic one for balance, is your center of gravity, where you can treat all your mass as being, is an important question in the balance of anything, and certainly in the balance of bicycles. All right.
Plus,
Go ahead.
Experience riding a bicycle.
Experience. You get good at it. You have to learn.
Yes.
I like it because it's a non-physical answer. But in a way, it's like thinking about, okay, presumably you get good at riding a bicycle. You learn what the dynamics are of a moving bicycle. No one really practices balancing on a bike when it's standing still. Maybe if that's all we ever learned to do, we'd be really good at it. All right, so guess what? I'm not going to tell you the right answer. There's a lot of places you can go and look. There's a Veritasium video. That being said, the thing that I am interested in as an educator, as a physics education researcher, is what did you do when you went about thinking about these theories? Chances are someone proposed an idea. Maybe somebody in your group had a physics class some number of years ago. So perhaps you had prior knowledge. Maybe also you thought about this as, I've rode a bike before. I have some intuition about how these things work, and I want to try and take my intuition and turn it into something that makes sense to me. Another element of this is reasoning, saying, well, did the thing that I said, did the claim that we made, did the things that we brought in from these other two kind of fonts of knowledge make sense with everything else? Is it internally coherent? So then you did maybe perhaps in your group assess the idea. You know, people challenge the idea of, well, maybe it's not just gyroscopic motion. Maybe it's more than one thing. You also have this idea of checking for consistency, where we're looking across ideas and making sure that one theory makes sense with another. Can we add two things together to give ourselves a more powerful effect, or do the two things that we're talking about conflict and disagree with one another? So, what's the point? All right, I asked you a physics question. I know a lot about physics. I also know how experts approach physics problems. So the way that experts approach things is that they generate an idea. They refine that idea through discussion, peer review, theoretical exploration, mathematical sense-making, and experimentation to validate results, to build on the model of physics. And ultimately that they check that it is consistent with every other physical model that we have. And what I'm going to note is that I don't know your body of experience. It could be that some of you know a lot about physics. It could be some of you know more about physics than I do. But I'm going to assume that quite a few of you in this room don't have a PhD in physics. You can correct me if I'm wrong. But I would note that a lot of you did very similar things. You generated an idea. You refined that. You thought about how it was consistent with other ideas about how things work, and ultimately you kind of checked these things against each other. Perhaps a group in the middle thinks about, well, inertia and gyroscopic rotational motion are not incompatible with each other. And then a group at the front says, well, what about when you ride a bike very slowly? And all these things serve to assess very kind of I'd say like informal ideas about physics. None of this involved us breaking out math. None of this involved any real formal physical theory other than what we brought in with us. So, a question that's going to underlie all of this is, well, what's the difference between experts and novices then? What's the difference between people who are new to something? Because it seems like you're doing the same thing. And the answer may feel obvious to you. Of course, physicists know more physics. Of course, they have more tools. Of course, they're more equipped to reason about these things quickly and to do this process over and over again very, very fast, and to toss their clicker. All right, so I'm going to pause for a second to do a little bit of meta commentary. Because today's presentation is on cognition. It's on how a mind works. It's on thinking about how to understand how we think. Why on earth is a person with a PhD in physics standing up here talking to you about minds? Well, once upon a time, I was an undergrad at Montana State University. And I had a professor who I hated. And he taught classical mechanics to undergraduate physics majors. And he had a thing taped to his board, and it started with this: America's most reliable, finest news source. If you know what this is, well, first off, he had an article from 2002 It's simply National Science Foundation, science is hard. Physicists actually love to pretend that they know everything, and I thought that this was a funny thing. It's like this professor who was telling us all about how great physics is and how hard it is to do was super proud to be able to say that he does science, and science is a hard thing. And if physicists love anything, it's that they love feeling smart. So I now have to prove to you, having just ego-checked myself here, that I actually know something about something. And that I'm not just up here to tell you as a physicist that I know everything in the world. What I'm going to propose to you is that physics, cognitive science, and educational psychology actually have a history together. And the reason is because a great way to study how people think about the real world, learn about the real world, is to couch it in the context of a physics problem. So as far back as 1908, we have examples of people discussing how people learn when you give them information about the way that the world works and how they apply that to something they actually do. So these two studies, Judd 1908, Hendrickson and Schroeder 1941, were studies of, I think, middle school aged boys where they were given a tank of water with a target at the bottom. And this is a little bit hard to see, it's a little bit small, but the idea here is that there's something called refraction in water. It's the reason why your straw looks bent when you stick it in a cup of water and look at it from the side. Light travels differently in water, and it causes objects within the water to appear closer than they are often. The idea here was that Judd, Hendrickson, Schroeder, all these guys gave middle school boys a dart or some kind of means by which to throw or shoot a projectile and asked them to hit a target underneath the water, and they did so while giving about half of them instructions about refraction, saying that, oh, you should keep in mind that this is how water works, that targets in water appear, I think actually maybe, I said closer earlier, appear further away than they actually are. And what they found is that these boys were able to more accurately hit the target when they had some information. They were able to transfer in this physical information even when they weren't explicitly told that that information applied to this particular experiment. More recently, we've had a whole bunch of studies throughout the 1980s with the emergence of something called the misconceptions movement, where people were looking at how do people learn about physics, about science, about the world, where a whole bunch of people were looking at what are the common misunderstandings when students take physics. And all of this was couched deeply in like the education literature of the time as people were starting to kind of think about, well, how do I apply this education literature specifically to my discipline, whether that's physics or chemistry or any science field. So we go way back. Having said that, I'm going to now make a huge jump, and I'm going to say, we're going to go from talking about physics problems to we want to model the mind. So what does this mean? Minds do a whole lot of things. What does it do? So I went through and just in like 5 minutes I listed everything that I could think of that a mind does. So a mind thinks, a mind learns, a mind recalls, a mind feels, a mind makes decisions, and a mind comprehends. I think all of these things are a little bit different. That being said, all of these things happen often all at once, right? None of these are totally separate from one another. Comprehending is related to learning. Thinking could be argued to be an umbrella for a lot of these things. Feeling may feel separate, but it's often intertwined with the way that we think, because the way that we feel often controls the type of thoughts that we are able to bring to bear. So, the mind does all of these things, and if you know anything about making models, at least in the scientific sense, you want to constrain your model to only cover a couple things that you care about. Because if you try to write a general theory of how the human mind works, you will have your life's work cut out for you, and some more. So, I'm going to tell you, here are some things that I care about. If I think about what our mind model should include, I've got 4 things for you. I'm violating the rule of 3s here. I should just have 3 things, but I'm going to have 4. So the first one is learning. I'm an educator. I care about how people learn. And I'm also going to put in here, and transfer. Transfer is something we'll discuss in a second, special case of learning. The second thing is something called context-dependent knowledge. It seems like you can know something in one context, and then when you're put in another context, you don't seem to know that same thing. You don't seem to transfer knowledge from one area to another. We'll talk about that in a second, too. The third is instruction-resistant knowledge. Chances are, if you've had, my understanding, I do not have kids. My understanding is that if you do have kids, you know about instruction-resistant knowledge. Despite being told something the same, repeatedly, the same number of times, it seems difficult to learn. It's true in physics classes too. And then finally, expertise. Getting back to my question at the very beginning, minds get better at doing things. How can we account for that? How can we make sense of why that happens? What is the mechanism taking place when your mind gets better at something? So let's go through all of these. I'm going to ask this very obvious philosophical question that is, what is learning, to start? We have to define it a little bit if we're going to make a model that encompasses it. I'm going to just keep it very basic. I'm going to say you have a brain. Sometimes that brain needs to learn something new. So I'm going to represent that with a little red dot. And we're going to say this little red dot needs to make its way into the brain. How that happens is open to interpretation. There's a million different ways you can learn something. That being said, you need to know something one moment that you did not know or understand prior to that moment. That is the act of learning, is growing in something that you did not priorly know. So the general question here is, how does this process happen? Our model we have a lot of ideas about this. Our model should tell us something about how this happens and should take into account the empirical knowledge that we have. That is to say, like the things that we see from observing how humans interact and learn together. So I said I'd tell you what transfer is. Transfer is a special case of learning. You might even be able to guess what it is from the name transfer. The idea is that this thing that you learned in the last slide is now present in your mind as you approach a new problem. Maybe you've made an excellent green bean casserole for Thanksgiving before, and now you're going to try and make a sweet potato casserole. Well, let's see how much of our knowledge transfers. One thing you can do is you can actively transfer. You can sit down and think about it like it's a riddle you're trying to solve. The other thing is that you could just go take a walk or a shower, and something along the way will happen. Maybe, in the background, if you've ever had this feeling of like solving a puzzle that you didn't priorly know as you're just out and about doing something, or having that feeling of something working in the back of your head, that's passive transfer. But the result of these is essentially the same. You take some knowledge you used to have and you apply it in some new domain. You have now figured out that a sweet potato casserole maybe shouldn't use cream of corn. I don't know. So, yeah. This is our learning category. Let's go on to context-dependent knowledge. I love this one. I'm going to read you a passage, and I'm going to put all of the text up here. It's a little long. Feel free to read along with me. I'm going to try and reveal it bit by bit. And I'm going to ask you, if you're able to make sense of this, this is like the first question. Don't immediately shout out what this is if you know or recognize this. But I'm going to go ahead. All right. So, if the balloons popped, the sound wouldn't be able to carry since everything would be too far away from the correct floor. And importantly, as I'm reading this, try to tell me what's going on. Try to make sense in your own head of what this is. So, a closed window would also prevent the sound from carrying since most buildings tend to be well insulated. Since the whole operation depends on a steady flow of electricity, a break in the middle of the wire would also cause problems. Of course, the fellow could shout, but the human voice is not loud enough to carry that far. An additional problem is that a string could break on the instrument, then there could be no accompaniment to the message. It is clear that the best situation would involve less distance, then there would be fewer potential problems. With face-to-face contact, the least number of things could go wrong. And I borrowed this passage from Bransford and Johnson, a study in the 1970s on comprehension. Does this make sense? I see heads shaking no. All right. So, this seems crazy. There's balloons, there's electricity, There's instruments. There's shouting, potentially. There's no face-to-face contact. There's lots of potential problems. All right.
Different types of communication.
Different types of communication? I'm going to show you a picture. Tell me if this makes it all make sense. All right. If the balloons popped, the sound wouldn't be able to carry, since everything would be too far away from the correct floor. A closed window would also prevent the sound from carrying, since most buildings tend to be well insulated. Since the whole operation depends on a steady flow of electricity, a break in the middle of the wire, and so on and so forth. Does it make sense now? Do you feel like you could remember it? So what Bransford and Johnson were studying is that they found that if people were given this image and then read this passage, they largely recalled most of it. They were able to understand it because they had some context to attach it to. Understanding the thing that you were reading had everything to do with being able to kind of match it to something in your head, some kind of schema, some kind of framework. So, yeah, this is where like the context comes in, right? This is like, if you have something in your brain that allows you to understand something in one specific context, you are more able to internalize knowledge about it. You're able to more quickly process it. Knowing that what we're talking about here is a very crazy serenade with balloons and a speaker helps you read this and make sense of it immediately, rather than reading this with no context and having no clue what's going on. All right, I have another example for you, and this is another physics one. So, context-dependent knowledge is all about knowing something and applying it in one space but not applying it in another. In a way, it's a failed version of transfer. And from a study in Hammer 2005, we're going to talk a little bit about Sherry. Sherry is an education student who's doing her master's, getting ready to be like an elementary teacher. And in one of her classes, she's discussing physics ideas so that she's ready to teach physics at a very kind of basic conceptual level to grade schoolers. Sherry has an idea in class, which is they're talking about mirrors. And the question is, how big of a mirror do you need to be able to see your whole body? And Sherry says, well, you need a mirror the size of your body, obviously. So you need a mirror that's as tall as you. Now, interestingly, Sherry comes back to class the next day and is a little bit downtrodden because she reveals that she went home and she looked at the mirror that she has, the full body mirror in her room, and realized that her full body mirror is not the length of her body. It's smaller. So Sherry didn't only know the answer to this question in one context. She purchased a mirror at some point that was shorter than she was. She stared at it every day. And yet, in her physics class, some other idea emerges. Some other thinking happens. So, and not only that, but that thinking that happens somehow trumps the everyday experience. So this is another way that context-dependent knowledge could show up. All right, third, we've got instruction-resistant knowledge. Some ideas stick around. Maybe, I heard some of you talking about very like physics-related ideas. Maybe some of you have taken physics class before. Here's a classic physical misconception. So if I have a ball, and I throw that ball up in the air, and we ask you, what direction is the force on the ball as it goes up after leaving the hand? The Newtonian physics answer for this is that the force is down. And I'm going to say that that's the correct answer. The reason is that force is the things that are pulling on or pushing an object. And after the ball leaves the hand, the only thing pulling on this ball is gravity, and it's pulling down. So, that being said, after Physics 101, at any university, you will still have some number of students who, having presented this as clearly as you can, having tested them on it, having spent a whole semester trying to build conceptions of what force is, will say, well, the force is up. It's moving up, so the force is up. We've tried as hard as we can. We've tried explaining over and over again. We've tried everything we can think of to try and get them to say this thing here. And still, some people seem to just kind of default back to this kind of conception of, well, the force is just whatever way it's moving. So this is instruction-resistant knowledge. You tell somebody over and over again to think of things a different way, and they do not. And the question is why? So finally, we have expertise. This is another interesting one. So a classic study from the 1970s is this idea of perception in chess, where people were looking at and saying, well, what makes chess experts different from chess novices, people who have just started playing chess? Maybe chess experts have really good memory, and they're just able to memorize things on the spot. They're able to see things very quickly. So what we're going to do is we're going to reveal a chessboard, and we're going to put this chessboard in one of two states. One of them is we're going to arrange the pieces completely randomly. It's just going to be chaos. It's going to be something that would never happen when a game was played. And we're going to show that state to the experts and the novices and ask them, after some amount of time, we're going to take it away, and we're going to ask them to recall it, to remake the board. The other thing that happens is that we show them a board that is an actual mid-game state. So like as if people have been playing chess for about 20, 30 turns, or somewhere in the ballpark where things have happened and the pieces have arranged themselves in a way that makes sense to one another. Some pieces are threatening one, some pieces are threatening each other, some pieces are safe, etc. And then we take the board away and we ask them to recall that. So what did we find is the difference between the experts and the novices? So first thing is that when we made the board random, the experts did not perform any better than the novices. So they weren't better at just memorizing things. But what about when the board was using like a mid-chess match state? Turns out the experts remembered everything. So a thing that experts do better is not that they just remember a whole bunch of information. It's not that they have a whole bunch of stuff that you don't. It's that it seems like they have the ability to see how things relate in their area of expertise very, very quickly. And the way that this was explained was that, well, because these chess experts look at the board and see kind of, oh, this is the current state of the game. These are the pieces that are being threatened. This is what I would do for my next move if I was this, if I was the white chess pieces or the black chess pieces. Those kinds of things and quick knowledge of those enabled them to recreate whole board states that they had only seen for seconds. All right, 4 things. All right, well, if you know anything about physicists, the other thing that we do is once we have all the parameters that we need, we try and brute force it. So let's just try on a few models. Let's think of how we could make a mind and how we could model it. So the first and most kind of like easy explanation would be to say we have the tabula rasa mind. Does anyone know what this means?
Blank slate.
Blank slate. Yeah. All right, you have a brain. It's empty. Starts empty. And you're going to pour stuff into it. This stuff is knowledge. So this idea that an empty mind receives knowledge. That being said, I think this one falls apart pretty quickly. So if we consider all of the pieces to our puzzle, the things that we really want to incorporate into our model, one of the things that's clear is that learning isn't passive. You can't just sit there and listen to somebody talk and receive all of their knowledge. If that were true, then our instruction-resistant knowledge would just not be the case, right? You would hear somebody say the correct thing, and you would internalize it. It seems like there's some issue where something occasionally prevents us from just downloading knowledge into our brain. Learning is not that simple, and it requires your participation. It requires your active thinking sometimes. So one way to deal with this is to say, well, maybe you have prior ideas that sometimes conflict with the new ideas. And this was the idea in physics in the 1980s, was that it seems like students have these naive concepts of motion that they come in with, these ideas about how the world works, and they hold on to those really, really tight. So the question then is, some people manage to get rid of those old conceptions and replace them with the new ones. Well, how do you replace old conceptions, and which conception will win? Because sometimes people hang on to their old ideas, and sometimes people hang on to their new ideas. I would also point out that an emerging problem with this is that this doesn't seem to correspond very well with our context-dependent knowledge theory. If people have really coherent beliefs about things, and they have these ideas that they come in with, that they've generated this whole theory of how physics works that is just based on their intuition, why do they say different things in different contexts? Like if you believe something, you would think that you should be consistent across different ways of expressing that belief. So maybe this is already starting to show some cracks. That being said, we spend a whole bunch of time in the 80s developing this theory. Fellows named Posner and Strike and Posner, come along with this theory of conceptual change where they say, if you have a belief and you have to change your mind, you have to do 2 things. One is that you have to recognize that your old idea doesn't work anymore, that it's faulty, that it's not able to explain everything that you observe. And then two, you need to find some new idea that clearly explains everything that you ever understood before, and also the thing that has made this kind of this first theory be faulty or not acceptable. All right. All of this happens. But in the meantime, in the background, there's some crazy stuff going on. So we're generating a model here, but we're also kind of talking a little bit about what is the history of these things. In the background, we have new ideas that are asking to be accommodated. We get to do Sesame Street today a little bit. We get to do C. C is for constructivism. If you've ever studied any sort of education, ed psych, anything in the last probably minimum 50 years, you've maybe seen this word. Constructivism is a theory of learning. And it's in response to this idea that learning isn't passive, that learning requires activity. We have this idea that knowledge is actively constructed rather than acquired passively. You have to make your new knowledge out of things that you already know. And then, yeah, that's the second bullet point. I just said it. New knowledge can be understood through connections to existing knowledge. The way that you understand things more quickly is by having more background knowledge in that area and being ready to accept another thing in and say, oh, that makes sense because it's similar to things that I already understand. And that's why it's very, very difficult for people who have not ever studied physics or any discipline to suddenly jump ship and go somewhere else, right? It's like if you haven't studied physics before, learning physics is hard. If you haven't studied chess, you're probably not going to beat an expert. The other thing that comes in is S. S is for society of mind. A fellow named Marvin Minsky is at an Ivy League school, and he's writing a program with these new things called computers, and they seem pretty neat. And he's trying to get this computer-powered arm to run a set of programs that will allow it to build a tower out of blocks. So he has a little camera strapped up to this arm, and he's trying to say, how can I make this arm run a program that will cause it to pick up blocks and stack them on top of each other? And he has the thought while he's doing this, well, it seems like maybe the human mind isn't all that different from what I'm doing here. So since computers are so cool, maybe if we treat the human mind like a computer, we can think about it in a way that allows us to model some of the things that it does well. So the thing that comes up in society of mind is this idea of agents and agencies. Minsky is writing tiny little programs and sequencing them together to get this robot to do some kind of bigger task. And so he's thinking about, well, maybe the human brain is made up of all these tiny little programs that are you're thinking on one of the things that gets activated is, well, I need to search for something. I need to find a block. So, a search algorithm or a little search agent is activated in your head. And you use your eyes to find a block. And then you reach out and you activate agents and agencies just being kind of collections of agents, as if you're running a set of programs together. You activate an agency to go out and reach out and pick up the block, and that tells your arm to move, that tells your fingers to be precise in how they grab something, and then it tells it to pick up the block. So in this idea is that, well, maybe human brains aren't actually super coherent. Maybe you're not always thinking about global beliefs and making sure that everything is consistent. Maybe you're sometimes just activating whatever resource you need, and sure enough, eventually we start calling these things resources, and that term comes from computer science. Maybe you're just activating whatever you need to make sense of anything in the moment. All right. So having now said that, let's go revisit our model of misconceptions. We might have a problem. This was showing cracks earlier, but now we have to think about constructivism. So we have misconceptions on one side, we have constructivism on the right. And what scholars begin to talk about when they look at these two things is that these two cannot be compatible. This idea that you have to take out an old belief and entirely replace it with something new doesn't really make sense, because really constructivism says that this old thing that you believed should be the building blocks for building something that is a new idea. So instead of viewing knowledge as one belief replaces another, in order to learn something, you have to somehow hammer and chisel your old beliefs into the shape of something new. And in some ways, that's liberating. In other ways, that's very, very difficult. So we're back to the drawing board. We need to find a constructivist way to make sense of all these things. And 3 fellows, John P. Smith and Andrea DeSessa and Jeremy Rochelle, write a paper called Misconceptions Reconceived, a constructivist analysis of knowledge in transition. 2 big words here, misconceptions, right? We already know what those are. And now we're talking about constructivism. We're doing a constructivist analysis of this old set of data, which was a way of explaining how people transitioned between ideas and made sense of new things. This fella in particular is important, DeSessa. We're going to talk about his ideas for a second because he's going to say a lot of important things. DeSessa's idea borrows from Minsky and says, well, what if we have cognitive resources? What if your brain is just made of little, small atomic ideas and you just activate whatever you need moment to moment to make sense of things? So if you're a novice physicist or a novice chess player, you start out with some kind of set of resources, and we're going to represent that in this graphic here as just kind of little shapes. These are the little ideas in your head, and these little connecting points with these dotted lines are the ideas that kind of connect these little things and network them. And when you start out, you have a few, and they're kind of loosely connected. But as you start to learn things, the shape of those resources begins to change, and more of them begin to be networked. And you see some of these connections become very, very strong. And you start to build kind of coherence across ideas. And eventually, when you're very, very competent, you've networked all of these things together in a way that makes sense to you. So the thing that enables physicists to very quickly make sense of physics problems is that they've spent a lot of time doing them, and when they see a physics problem, they very, very quickly call to mind all of the relevant resources, all the relevant tiny little programs, and it's because those connections between ideas have been strengthened over time, whereas a novice doesn't have those things. The key difference here between the misconceptions and the resources framework is that resources says whether you're a novice or an expert, you have the ability to do these things. It's a question of how quickly you can do them, how well you can find them on your own, so on and so forth. So going back to the first, the first question that I asked, I kind of made this point that a lot of you did things that were similar to what experts would do. And that's the point of resources, is that people who are not experts still possess the ability to do expert-like procedures. So let's talk a little bit more about this. DeSessa calls his resources, specifically for physics, something called phenomenological primitives, which the field immediately abbreviates to p-prims, understandably. So what are these? This is like a deeply academic philosophical term. But basically what p-prims are is that these are very, very basic ideas about how things work. As it turns out, all of you grew up in a world that obeys the laws of physics. And what this tells us is that you learned things about the physical world that are pretty much true given the context. So you have some basic ideas about how things work, and we'll get some examples of that in a second. Whenever you need to make sense of something that happened in the physical world, you call upon your p-prims. You have a whole set of them. And these things are not inherently right or wrong. They're just tools for making sense of the world. So sometimes you organize your p-prims in a way that helps you perfectly understand a physics problem. Other times you organize them in a way that leads you to think that force is the same as velocity or movement. So an example is here, if I move my hand close to a fire, right? Something that you learn at a very young age is that when something is very hot, the closer my hand gets to it, the more heat I feel, to the point that eventually it becomes uncomfortable, or to the point where eventually I burn myself. And this gives you a very basic little atomic idea about the way that the world works. And that idea is, the closer I am to something, the more I feel of it. And that idea is reinforced with things like, maybe as a kid you hold magnets together and you realize that when they're far apart, they don't pull on each other really at all. And the closer they get, they start to really grab hold of each other. So this idea of closer is more, it's a simple idea, and we see that idea emerge a whole bunch in physics. How does gravity work? Closer is more. How does all of electrostatics work? Closer is more. It's all this. So this basic idea is reinforced over and over again. All right, so we've got our resources model. You have some resources in your head, you tie them together, you do different things with them. We're also going to call this idea knowledge in pieces, by the way. That's what DeSessa used to describe his term. More broadly, we use resources to talk about them now. So how well does this model capture all our considerations from earlier? We had all these things to talk about. Let's go through these quickly. So first thing is, let's talk about 1 and 4. We've kind of already talked about this. learning in the resources model isn't gaining things that you didn't already have. Maybe there's a little bit of that. You can see that there are more shapes in this second than there are in this first. But it's about networking things that you already have. The ideas that you already have for understanding how things work get slowly kind of pulled together and grouped into framings and things where you understand how the world works a little bit better, or understand how chess works, or understand how fishing works, any set of things that you might do. As you become better at it, you become more able to process information about that or to interpret information within it quickly. And then learning is really just the process not of gaining new things, but of networking those things together. So, does this explain context-dependent knowledge? The answer is yes. Let's think about Sherry again. Well, Sherry simply activated different resources in different contexts. Resources are really built for this kind of paradox where people don't apply things in one area that they applied in another, because it just means that when you shifted context, your brain is not some coherent being that understands everything and sees how everything fits together. It's going to reach out and grab whatever it can to make sense of what it's being presented with in the moment. So Sherry, when she was thinking about a mirror in a physics class, maybe was transferring in knowledge of doors. Maybe she was thinking about a door. A door needs to be as tall as me to get through it, and it's a problem sometimes. When actually, there are other resources that you can think of. Is if you think of a mirror as a window, well, it's clear that I can see a tree out my window that is not the same size as my window, right? So different sets of resources, different ways of making sense of things are activated depending on the context. We have ideas as humans of what knowledge is most useful, and we apply whatever we have given the moment. And then the last thing is instruction-resistant knowledge. How does this make sense? Well, if we compare the beginning to the end, one of the things that happens as you become more and more of an expert in something is that you begin to build something called coherence. And what happens is that as you build coherence, your ideas become more self-consistent with each other because you become more able to do things like say, oh, gyroscopic motion is enough to keep me upright when I'm riding a bike, but when I'm riding slow, then something happens. I'm still able to go forward, even though the gyroscopic force on a slow bike is not nearly as big as a fast bike. So comparing across these sides gives us an ability to say, well, the thing that novices lack that experts have is coherence. They haven't yet been able to recognize that, oh, all my resources, all my thoughts about this thing need to stick together. And this is a feature of novice behavior and newcomer behavior in a lot of hobbies. Certainly in physics, and certainly also in chess and other things. All right. So, if this is true, what are the implications? So this is where I'm basically going to end. I have the thoughts on implications for 3 different spaces. One of them is cognitive science. One of them is education. One of them is everyday life. All right. So for cognitive science, we are still doing a lot to grasp what even is it that human minds do. We know very little. We know a little bit about neural networks, but we have no general theory for how people think. That being said, this is a pretty good framework, though it has one problem. It's unfalsifiable, but it's a pretty good framework for exploring the way that people think and learn. The problem with something being unfalsifiable is that it's actually really difficult to say, oh, the human brain doesn't work this way, right? I can go out and look for a million resources, and I can continue to explore this thing. And so long as it is useful, that's good. But it doesn't really make predictions. And typically, maybe if you were here last week, you talked about this, one of the key things in order to test scientific theories for validity is to see if they make predictions that you can then go and test and find to be true. This is just like a convenient way of thinking about something. And it makes sense with all of the things that we look at, but it probably has its limitations, and it's difficult to find where they are. So I'm going to say that this is a good way to think about things, but you have to be careful of how far you apply it. Like any model, it will break down at some point. Having said that, I'm now going to tell you how to apply this broadly across multiple contexts. So the first is education. This is the one that I thought about a lot. I wrote a dissertation on this. So in education, the resource theory encourages us to think about students' ideas not as being inherently right or wrong, but as students who are people and who are making sense of things as they go. They're trying to pull on resources that they are still kind of developing. They're really not particularly, like they're still building their expertise in a lot of areas. They don't know a whole lot about how the world works, but one way that we can help them build that is by recognizing what they do know and kind of come alongside them, and rather than trying to kind of correct them and make them think the way that we do, we want to try and embrace their differing conceptions and also their process of understanding.
Question.
Answer. Sure.
So you're saying a better way to teach would be to present knowledge and then give a physical example to reinforce that idea?
I think that that is one way to do things, certainly. I think that also the most radical version of this is something called responsive teaching, which is about where the ideas that the students have and helping them test their own ideas and build their own ideas becomes a key part of the curriculum. So you say well, rather than, the classic example of this, I'll talk about this in a second, is, and we're basically to questions anyway, is an academic named Deborah Ball did a study of a math classroom in which she taught, where a student named Sean made a claim that he thought that the number 6 was both even and odd, which is a strange claim, and if you know anything about numbers, numbers cannot be even and odd. But she said, well, oh, Sean, tell me about your idea. And what Sean was thinking about is, well, 6 is actually, it's made up of 2 sets of 3. And 3 is an odd number, so 6 contains an odd number in it if I break it down into its prime factors. And so what Deborah Ball did is she said, well, as a way of now getting my students to think about how these things relate to each other and how to evaluate ideas, let's go exploring for a second and find as many of these Sean numbers as we can. So that's the most extreme version of this. But showing people a physical example as a way to kind of give them something to latch onto in their own way is another way of doing that. There's a lot of ways to approach this. Right.
Although I disagree with you that there isn't a quote-unquote number that's both even and odd.
Oh, there's a number that's both even and odd?
Infinity.
It's not a number.
True. That's quote-unquote number.
Okay, quote-unquote number. All right. I'm going to give you the last thing here. So this is the last thing that I think about a little bit, is this idea of cognitive resources as they apply to everyday life. Because I think that studying this model has made me think fundamentally differently about how I interact with people, and I'm still feeling challenged by that. So if humans are prone to activate different resources in different contexts, that means that humans are inherently contradictory beings.
Just finding that out.
Okay, no, just finding that out, you said. Here's the thing. We have always known this to be true, but I think that the comfort I had in this was saying, oh, this isn't an inherent moral failing of people. This is a thing that we all do when we don't know much. We all just kind of reach out and grasp for the nearest thing. And so all of a sudden it makes sense why people can say one thing in one moment and do another. It feels to me like oh, I understand a little bit more why it is that I have people who feel very compassionate in one context, but then when I see the things that they advocate for politically, I find those to be disastrous or very uncompassionate. And I'd say that very generally, I could talk about this for a long time, but I think it's really important to think about how we can seek common understanding, how we can say, where are people coming from? What are the presuppositions? What are the things that are active in their own heads? And how can I understand those before trying to assess where people are right or wrong? All right. In very, very tiny text, which you can see if you scan the QR code, these are all of the things that I referred to. I wouldn't expect you to read all of these in the moment. But that being said, I put those at the end if you want to check on them. QR code's right there. I have been Sam Engblom. Thank you for having me today. All right, we have 3 minutes for questions.
DeCessa, talk about in the brain and making the neuron connections and stuff. Like a tabula rasa. But, say, as you look around, say dog breeds are born with certain tendencies and instincts and stuff, and we have instincts and stuff and such too. How does he account for such things and say, every brain is born with certain instincts?
Yeah, that's a good question. So the question is like, when we look at like different, whether it's like animals or things, it seems that there is some kind of like genetic memory, or there are things that you are born knowing. How does good old Andy DeCessa account for those things? I don't totally know the answer to that, but I think that one thing that people would say is that this is kind of like the classic question of constructivism, is that if you need to make knowledge out of things that you already know, you need to start with something. So one thing would be to say, well, maybe, from your genetic history, you have some basic ideas about things that you are born with, that your brain kind of comes pre-constructed, and that you're going to use those basic tools to start grasping things like, you're going to start making sense of language, you're going to start making sense of human faces. Another person who did studies in this area was Susan Carey, who I cited in here. She was actually the one from whom I pulled the serenade picture. And she studied how children had developing ideas of what alive meant, of like in biology, of like what it meant to be alive, what it meant to be dead. So I think that there are certain things like that everyone acknowledges like that have to be inherent to this. You have to start with maybe something. But certainly it's true that like humans seem able to develop these conceptions in a more sophisticated way than any other form of life that we know.
Thank you.
You have a question in the back?
You didn't have anything about the senses. It seems like we take in a lot of information that way that we also combine with everything else.
Yeah, that is a whole other topic that you could spend a lot of time on, right? I think that the most that I touched on it was to say that these P-prim ideas that DeCessa had are largely acquired through senses. It's like you kind of understand things about how the world works because, again, like you held your hand closer to a fire as a kid, and eventually you found that it's like the closer you got, the more you felt. Then they have these ideas of like, oh, I've experienced gravity all my life. I have this idea of like what goes up must come down. And, people go through lengths to, yeah. Yeah, people go through, yeah. People go through lengths to study these various things and to try and catalog how many different resources people have for understanding any topic in physics or science or biology or what have you. But a lot of them, when you get down to the most basic elements, are grounded in things that you would experience through your senses, like things that you could see happening, things that you could observe happening, characterizing the way that you think about the world. Yeah. Question?
If you're learning how to play the piano, the phrase of practice makes permanent, whether it's correct or incorrect, is permanent. And thinking about that in terms then of who we associate with, what we're doing, kind of the echo chambers we get involved in, it seems like it's laying down those pathways in the brain just over and over. It's the same kind of permanence. Is that along that lines?
Yeah, I would say that that's generally true. So like the more that you do something, you're saying like from piano, it's like you have the idea of practice makes not just perfect, practice makes permanent. And I think that that's like, I think another compelling thing about these resources is that it feels like the model we have matches up with kind of the structure that we expect from the brain biologically, right? And so like, you have neurons that build stronger connections as you activate them more. And so it makes sense to me that like a difficult thing then is that like, you have the instruction resistant knowledge. Resources don't care about whether an idea is right or wrong. The ability to evaluate those things is a human construction, right? Newtonian physics is a model we constructed, but so are, models of sociology, politics, like human relationships, anything like that. So I think it's possible, the more that you have something reinforced to you, the stronger that those connections become. And oftentimes also the more coherent. You begin to say, oh, I'm going to now try and make sense of other things in light of the things that I understand very, very well and completely. And certainly the problem with that can be then is like, if I have a conception that is not grounded in reality, one of my ways of making sense of reality is to say that my perception actually leads reality. Like the things that I perceive to be true are now more important than what I see around me. Yeah. All right. So I think this is over. If you have more questions, I will happily stand up front here and take them, but I feel like we should just properly end this and dismiss everybody. All right, thank you all. It's been great.